The objective of this video is to define electric loading and relate it to the equivalent circumferential current density of an AC machine. We're going to start by considering an electric machine that has a circumferential current density on it, and we're going to build up to the concept of a linear current density when we unroll the machine and turn it into a linear machine. And then we're going to use this to develop the parameter of electric loading of an electric motor, which is a fundamental design property of motors that's independent. It's an inherent property of motors that's independent of the size of the motor that you're constructing. So let's start with this machine that I've sketched on here, which you see it has a rotor, it has a slotless stator, and then on the inner bore of the stator I've placed some kind of circumferential current density. And if you recall, the circumferential current density is a distribution of conductors with current flowing in them, and so it tells you the total number of amp turns at any angle alpha. And if you recall, we can relate this to a current density and integrate it to calculate the total current flowing through some surface. So if we were interested in calculating the total current flowing through this surface here, we would evaluate the current density over that surface, or since we have the surface current that's on the inner bore of the stator, we actually just have to integrate that surface current from alpha 1 to alpha 2. So if this is alpha 1 and this is alpha 2. And this is just a reminder of what this is. So what is the physical justification for talking about a distribution of surface current? In our previous videos, we've been talking about line currents or surface currents that only exist at an infinitesimal point on the stator. Now we're going to be considering this as being a continuous distribution, and what is the justification for that? What does that mean? Well, you can imagine two situations where this is valid. The first is completely a physical system where you have actually a slotless stator, and you have exactly what I've drawn here. So if you have a slotless stator, oftentimes you will put on the inner bore of your stator kind of a woven mat of conductors. So it'll be a continuous distribution of conductors that are very thin and literally glued onto the stator. And so in that case, you would actually have this continuous distribution of amp turns on your inner bore of your stator. And the second case, or the more general case, is that if we make a graph of what our circumferential current density actually is, we can consider it to exist only at the slot openings of our machine, or it could be spikes like we talked about before. So if you consider that you have some kind of winding, and then you have these narrow pulses where you've got your current density appearing, and you can review your previous lecture to help understand this, then you can start to think about this quantity, the circumferential current density, as being represented by a Fourier series, as being a sum of harmonic components. And we can relate this figure to what we drew in our previous lecture, where we noted that our linear current density, our surface current density, is going to appear within these slot openings here, and then not at all on the surface of our teeth, because that's an equipotential surface. So we made that comment before that you can define your linear current density or your surface current density by dividing the total ampere turns in the slot by the slot opening. And so if I draw some lines here, we could say that this is slot 1, and this whole region right here would be this right here. And if this is slot 2, that's right here, because remember, we're walking around from alpha equals 0 to some larger value. And then according to this drawing, that means that we'd have conductors going this way in slot 2, and then slot 3 would have conductors going into the page, because that would be this negative pulse over here. And again, just the slot opening area. Okay, so that is what we talked about last time for surface current density, or circumferential current density. This time we're going to start talking about a linear current density, and we can make the observation that we can take our slotless stator up here, our example machine in the top left, and we can unroll it to be a linear machine. And so if we do that, if we start at alpha equals 0 again and we work our way this way, we can draw what our stator looks like. It's now a flat plate, and our rotor is a flat plate. So on the left side we have alpha equals 0 degrees, and on the right side we have alpha equals 360 degrees. And as we go around this plate, we have conductors. And I'm just drawing this in a general sense. I am only drawing conductors here to indicate that there's some general current density at this location. And now instead of being a circumferential current density, it's a linear current density. So this is our stator at the top. At the bottom we've got our rotor. And we're noting that on the inner bore of our stator, which is now beneath the surface of our stator, we have got a linear current density, A of alpha. And we can do some mapping here to notice that the length as we travel left to right is equal to our rotor's radius times the angle that we're traveling. Or in the nomenclature of the book, is equal to DOR divided by 2 times the distance that we've gone in radians. And that's just observing the fact that when you have an arc of angle alpha, the linear path, the path that you take like this, the length of it in meters is going to be alpha times the radius of that arc. So what is a linear current density versus a circumferential current density? In a general sense, we've been talking about the total current through some surface as being the integral of j dot ds, the current density over that surface's area. And we've noted that if we have a circumferential current density instead of a general current density, we have a line integral over an arc. And if we have a linear current density, that means instead of a line integral over an arc, we just have a line integral over a straight line, over a path. And you'll notice my nomenclature here. I'm indicating a circumferential current density as AC, but a linear current density as A. So we can notice from this that we end up having a differential current at any angular location alpha as being our circumferential current density times d alpha, which is clearly equal to our linear current density times our differential length that we're integrating over. And from this, we're now ready to relate our circumferential current density to our linear current density by solving this equation for A of alpha. And we get this relation that our linear current density is going to be 1 over our rotor radius times our circumferential current density. So when we had our electric machine, we talked about the fact that we were putting conductors in slots and that we can construct from this an equivalent circumferential current density. Now what I'm telling you is you can take your equivalent circumferential current density and you can construct an equivalent linear current density for considering this as an unrolled linear machine. And just as we can talk about our circumferential current density being decomposed into its various frequency components, we can do the same thing for the linear current density. In all of these harmonic decompositions, every time we take the Fourier series of a waveform, we consider the fundamental component, in the language of the machines community, as being the component that occurs at n equals p, at our index equal to a number of pole pairs. So in general, if you have a waveform for current linkage or your equivalent current density in the inner bore of your stator, the true fundamental of that, in the sense of a Fourier series calculation, is going to be 2 pi. It's going to be from radians of 0 to 2 pi, because that's one revolution around your stator. But in electric machines, we typically have periodicity based on the number of pole pairs of our machine, and so the convention is to call the index of n equals p as the fundamental. And so again, this is a frequency decomposition, so we can talk about our fundamental component as being a sinusoid with a certain magnitude, and we're calling that alpha AP peak, AP hat. And from this we go back and convert it, of course, to our circumferential current density. So where are we going with this? Why are we doing this? Well, it turns out that this quantity AP hat is a fundamental property of electric machines. In fact, it's referred to as the electric loading of the machine. And it's important that we can trace this back and forth to the physics of our machine and the actual wires that we were putting in slots. So we started off by talking again about slots, conductors in slots, and how from that we can construct an equivalent circumferential current density. And then we started to say, well, we can use that and convert that into an equivalent linear current density. And now we're going to relate the peak of that linear current density back to our circumferential current density and the actual physics of our machine. And we're going to be doing that in subsequent videos. In this video, we're just defining this concept of electric loading. So this is referred to as electric loading, and it has units of amps per meters or kiloamps per meters. It's often expressed as an RMS quantity, so it might be kiloamps RMS per meter. And this property of a machine is a very general property. It turns out that you can talk about the electric loading of a machine for any size motor, independent of the rotational speed and independent of the diameter or length of it. It's similar in nature to what we introduced previously as winding functions being an inherent property of a winding. The electric loading is an inherent property of electric machines, and you find that you can achieve only a certain range of electric loadings as limited by your ability to draw heat out of the machine. So electric loading is directly tied to the thermal management of your machine, your cooling capability. And so I'm going to refer you to your textbook. Table 6.3 gives a range of typical achievable electric loadings for different cooling situations. And the table will show you that typically for air-cooled machines, you can achieve between 30 and 80 kiloamps RMS per meter. And if you're using liquid cooling, you can usually get between 90 and 200 kiloamps RMS per meter. So why do we care about this? Well, we're going to show you in a later video that electric loading and your magnetic loading, that is your magnetic field and your air gap, are directly related to the torque capability of your electric machine. And when you're a designer, you're going to start with an inverted problem. You're going to be told that you need to achieve a certain power rating at a certain speed, which tells you that you need a certain torque rating. And maybe your customer also says it needs to fit into a certain form factor. And if you know that your electric loading is directly proportional to your torque, you can make some design decisions immediately about what kind of cooling system you need. So if you see that your magnetic loading, your magnetic field and your air gap is limited to a certain value, then all of a sudden you know that you have a certain range of electric loading that's going to allow you to get to the torque that you require. And based on that range, you can see whether you can get by with air cooling or liquid cooling. So this whole video is using analysis to build up the concept of electric loading, but then giving you a tool that you can use in a design process to figure out what kind of system you can use to meet your customer requirement. All right, let's summarize. So in this video, we've introduced electric loading, and we've related it to the equivalent circumferential current density of a machine. And we've noted that the equivalent circumferential current density of a machine is directly related back to the physics of the machine, the actual conductors that you are installing in your motor. We've sketched some diagrams for how this looks, and we've come up with our relation down here. And then noticed that we can decompose this into its harmonic components. And the fundamental component is the component that appears at the number of pole pairs of your machine. And then defined this fundamental component as being the principal electric loading of our motor, and talked about how we can relate that to well-established design rules of thumb for what you can do based on your cooling level.